All right, so we're going to continue on in our kind of journey through color mixing, and we are going to talk about complementary colors. Now, the definition of complementary colors is just two colors that neutralize each other when mixed in equal amounts or measure. Okay. Now, if complements are made of light, when you mix them, then white light is what you get. If complements are paints, they make a neutral color when mixed, and the neutral color kind of depends on like what you're mixing. Like violet and yellow, generally you get a brown. You can also get some, you can get black. Generally, when I mix green and red, I tend to get more of a black color. Blue and orange, I tend to get more of a brown color. And so when we talk about this mixing, it's also called desaturating. However, so we don't want to mix them necessarily unless we're trying to get a brown or trying to get a black or a desaturated color. But one of the things that we know is that when complementary colors are next to each other, the colors appear to be enhanced. And so, or they pop, right? They just appear to be more vibrant and brighter. And so when we, maybe, if I can get this to move, it's moving one thing but not the other. Okay. So when we think about this, we see this a lot in marketing, right? So this is a color wheel. Complementary colors are across from each other. So red and green are complementary colors, blue and orange, yellow and violet. And so if we look at red and green, because these colors are enhanced when they're next to each other, that is a lot of times what you see in marketing. So like strawberries are placed in green baskets to make the strawberries look brighter, which of course makes us be more appealing. One of the artists that's really well known for using complementary colors is Vincent van Gogh, right? And so when we look at some of his painting, and you know, a lot of us know Starry Night, but when we look at some of his paintings, you can see here, there's yellow and blue, or kind of more of a orangey yellow blue that is being used here. We can see the red hat on the green. We can again see the orange and blue here, which are those complementary colors. So he's really well known for using complementary colors next to each other. And so that's a good example. Now, let's dig around a little bit more into color context just for a second. So when we talk about color context, one of the things to be aware of is that, or what this really means is that the colors that are around a color will either can change your perception of it. Okay, so for example, this red square is the same in each of these blocks, right? But it looks enhanced or sharper or better or more saturated. It just sort of depends on the verb you want to use when it's next to certain colors. Like it really pops here, but it's duller here. Okay, it tends to pop here. So this idea that the things that are around a color can influence it have been studied quite a bit by a guy named Joseph Albers. And we're going to talk about him in a second. But I wanted to show you another color context. And this one I think is really great. So when we look at this, these two purple squares here are the same, right? But they look like different colors, right? Because of what their background is. Now, as I mentioned before, Joseph Albers was a famous artist. He really worked on this. That's him and his wife, and I love this picture. They're very much in love. She was an artist in her own right. Her name was Annie. So Joseph and Annie Albers. And together, she was really a fabric artist where he was more interested in paint, but they were both interested in color. And so they wrote a book called The Interaction of Color. If you want to fall down a great wiki hole, reading about their life is just kind of interesting. He fled Nazi Germany. He ended up in the U.S. He ended up at a new college in North Carolina. And then, of course, ended up at, I feel like he ended up at Yale. I did not write that down. I probably should have. And so he was an abstract artist that experimented with color. He has an app. This book is now an app where you can look at color and move squares around to see what colors enhance a certain color. So like I can move a yellow square into a different spot to see that. And I'm hoping I'll be able to show you that in class. If you are interested in this, there's a great YouTube video to watch on them. And then there's still an Albers Foundation. And so that's a really great place to just find out a little more about them in particular. But he really looked at color complements, right? Now, let's talk a little bit more. So we talked about how we can place colors. Let's talk a little bit more about color mixing. And so there's two different types of color mixing. One type of color mixing is additive color mixing, and the other type of mixing is subtractive color mixing. Now, additive color mixing basically describes how the colors of light mix together, right? Now, this is the basis for how color is created on computer screens, TV, LEDs, etc. Stage lights in a theater, any other sort of light source. When light travels to our eyes, our retina is going to add together all those different wavelengths that our cones are sensitive to and compare the activity in each. And the result of that is that perception of a particular color within the visible spectrum. Now, when all of these lights are added together, you'll see that it turns white. And my hope is that you'll be able to do this in lab. I have some green, red, and blue lights for you to mix together. And again, my hope is that you'll see white. Now, another thing that we're going to do in lab is some subtractive color mixing. And so when we talk about subtractive color mixing, this is what happens when light comes to us indirectly because it hits a surface first. Okay, so light comes to us indirectly because it hits a surface first. Okay, so and I'm showing you this here with this image. And so basically what happens is some of the wavelengths of light are absorbed, right? And when they're absorbed, they are subtracted, hence subtractive color, okay? And then some of those are reflected back into our eyes, and that's the color we see. So when we talk about subtractive color mixing, this is for pigments and paints. Because we're adding, what we see there is, instead of adding wavelengths when they mix, we see more absorption, and that changes the color that we perceive. So imagine you have white light hitting a surface, and the white light, of course, is made up of all the colors of the visible spectrum. When the white light hits the surface, some of the colors of the visible spectrum are absorbed, and others are reflected back, right? When a color is subtracted from white, then another color is revealed, right? So if the surface subtracts red wavelengths from the white light, we end up seeing cyan, right? So if we're subtracting red, we end up seeing cyan. If a surface subtracts green from white, we end up seeing magenta, right? And if a surface subtracts blue from white, we end up seeing yellow. If all three colors are subtracted or taken away, those wavelengths, then we see black, okay? So, for example, light hits the pigment in this paint can, and every color in the visible spectrum is absorbed by the pigment except for red. And so those absorbed colors are subtracted from the light, and only the red light is reflected. Now, so those are those two color modules. And when we talk about how we see light, one of the things that we will run into is different ways we see light, for example, on a computer screen, right? And so when we talk about this, RGB is referred to, and this stands for red, green, and blue, okay? And it's the color model using light, right, in TV, right, in computers and tablets and phones, and basically any sort of display technology. It was also used for the first photographs. Now, today's screens are made up of individual pixels, each with kind of a red, green, and blue light. Most TVs now, these are too hard to see with the eye. I can remember, because I'm older, we had older TVs, and we could get really close and see the individual pixels, with the different colors. But now you probably need a magnifying glass to be able to see this. So if you were, for example, to see a purple flower, you could put a magnifying glass up, and what you'd actually see are the red and green and blue pixels. If you took a step back, that purple flower would appear again. Now, this RGB is based on the additive color system, right? Where red, green, and blue light mix to create millions of other colors of light, including white. And we can see this is a kind of a cartoon of how that works here. For red, we just see one pixel, green and blue, we just see one pixel. But for example, if you wanted to get cyan, you would mix the blue and the green. If you wanted to get a magenta, you would mix the blue and the red. And if you wanted to get a yellow, you would mix the red and the green. Of course, if you want to get white, you would mix all of them. Now, the RGB can produce just a huge amount of color. This is very simplified because it correlates to the three kinds of cones in our retina that are sensitive to those long, medium, and short wavelengths. And so that's an example of additive light. Now, another type of system that we'll run into that combines colors is CMYK. This stands for cyan, magenta, yellow, and black. Okay. Now, if you look at this, you can say, okay, I see the cyan, the magenta, and the yellow, but that's not a B there, that's a K. That K stands for key plate. Okay. And that's just a plate that's responsible for the detail, which is the lines and contrast of an image. In a typical 4-process printing, the key plate is black, and so that's where that black comes from. Now, today, most printers create colors we see on a page through these tiny dots of cyan, magenta, yellow, and black. And the dots are so small that close together that our brains see them as a continuous field of colors. So the overlay would give us something like this image here. So here are the individual images. Typically, each color is printed as a separate plate. And just like with a computer screen, a print made with the CMYK process may appear to be a full image like this, but if you were to put a magnifying glass up to the paper, you'd see the individual dots of the 4 colors, nothing really else. Now, this is an example of a subtractive color system where these inks are used to create millions of colors, and we're mixing them in the kind of, instead of light, again, we're mixing pigments. Okay, now I want to point something out here that's kind of interesting, is pointillism. Now, pointillism is paint, okay? And so your first thought might be that, okay, well, if it's paint, it's subtractive. And so when we look at the pointillist movement, George Seurat basically utilized the concept of visually blending colors to make these paintings. This is one of his most famous works. This is Sunday Afternoon on the island of La Grande Jatte. I'm sure I'm mispronouncing that. And there's a woman that's powdering her face. And if you zoom in to these paintings, what you'll see are individual dots. And I chose this one because it's individual dots of red and green. Now, if those were mixed in a subtractive mixing, red and green would give us brown, okay? And so when we back up to see an image like this, which is like up close, you can see an image like this up close on her face, for example. But when we back up and our brain says, okay, that's the image of a face here, there are no real mixing of pigments to produce the muddy color. Instead, your eye, or the eye of the viewer, blends the colors that are in close proximity. And because you're blending these colors that are in close proximity, this is an example of additive color mixing. And he also used some subtractive color mixing with preparing his paints, but the reason that we see kind of these dots that turn into images, besides the fact there's spaces there and our brain fills in the gaps, the reason our brain fills in the gaps is because of the additive color mixing with the light, which is just kind of an interesting exception, I think. The other kind of interesting exception are Maxwell discs. We're going to mess with Maxwell discs in class or in lab. When you go to the movies, for example, you're viewing a series of still pictures which appear to you as motion, and your brain interprets these frames, which move about 16 per second, as continual motion because of vision persistence. The eye-brain apparatus holds each image for about 1/10 of a second. So each still frame is overlapped onto the next one to give an illusion of motion. Okay? Well, in the 1800s, James Clerk Maxwell, who's this guy here, who was a Scottish physicist, found that vision persistence could also happen or cause the blending of 2 distinctly separate colors. And so to experience this, which you'll do in lab, what you're going to do is you're going to take a disc, something like with 2 colors on one side. We're going to put a pen in it. We're going to spin it rapidly, and we're going to see that these 2 colors combine to give us a different color. Now, you can think of this as kind of an area of color on the disc as sending a beam of that color light to your eye. And the 2 different beams of light are being mixed by your eye brain to produce, by your eye and brain, not eye brain, eye and brain, to produce a new color. So because you're talking about mixing colored lights, because that's what you're seeing coming back to you, this is also an example of additive mixing, color mixing. So again, we'll get to do this in lab. and try out some with our color project. We'll get to try out some different types of mixing, both additive and subtractive.